So every once in a while I get the urge to write on a blackboard, so I thought I would do this video, pretend as if I am writing on a blackboard. And so that is why I've got this nice Wacom tablet, and I can have some fun with that. And so okay, let me get rid of some of the stuff that I just did. So today I want to talk about complex numbers, and it has recently, not recently, but it has occurred to me over the years that complex numbers are in fact the biggest blunder. Now, not complex numbers themselves, but the way that they have been taught and the way that they have been interpreted in various fields. And so I am beginning to feel like actually complex numbers are responsible for all the confusions in the language. And as I say many, many times, the problem is with the language. And so I am beginning to believe that the way we represent complex numbers is a cause for confusion, and that is getting injected into the language of theoretical physics. So complex numbers are the biggest blunder, not complex numbers themselves, but the language that we use to describe complex numbers. So what I'm going to do is I'm going to teach you complex numbers, only I am not going to use any of the legacy language whatsoever. I'm not going to use real numbers. I'm not going to use imaginary numbers. I'm not going to write down the letter I unless it appears in the word sine, as in sine and cosine. Okay, so I as an imaginary unit is not going to be writing the letter I. And so I am going to teach you complex numbers without using any of the legacy language. Okay. So the first thing you need to realize is that complex numbers are two-dimensional numbers. Okay, so mathematically you need to set up a 2 by 2 matrix to hold a complex number. Okay, so I use square brackets for matrix, and there's going to be 4 entries into this matrix. Here, 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 and here. Okay, that should be an X matrix. So complex numbers are two-dimensional numbers, and in order to represent them completely and unambiguously, you need to put them into a 2 by 2 matrix. Okay, and there's going to be a number here. Okay, let's call that A. And there's going to be a number here. Let's call that B. Okay, and here's where it gets a little tricky. In a complex number, if you put A here and you put B here, you have to put minus B here, and you have to put A here. So this is positive, this is negative, and these two are the same. And so this is the complete definition of a complex number that exactly corresponds to the legacy equation A plus BI. Okay, so you've got 4 entries in your matrix. You've got 2 values, 2 unique values, A and B. Okay, on the forward diagonal, the values have the same sense. You can see if this is positive, this has to be positive. If this is negative, that has to be negative. Okay, and on the backward diagonal of this 2 by 2 matrix, you've got if B is positive here, it has to be negative here. But if B is positive here, okay, if B was positive here, it would have to be negative there. And so this is it. This is the best and most complete representation of complex numbers. There's nothing better than this. Everything else is just notation to look pretty in a paper, A plus BI looks much prettier than this, but this representation is 100% complex numbers, 100% complete. You don't need anything else other than this representation to do any operation you want to in using complex numbers. So I'm going to clear the slate and start again, only a little more carefully. So what I'm saying is with legacy, in the legacy language, complex numbers are written like this. So a complex number is written like this: A plus BI, where A is some ponderable floating point value, B is some ponderable floating point value, and I is the unit of the imaginary numbers, and i.e. it is the square root of -1. Okay. So the way I would prefer, the most transparent way of representing complex numbers is in a 2x2 matrix. Okay, so to write this, I would write A in the upper left quadrant, B in the upper right quadrant, minus B in the lower left quadrant, and A in the lower right quadrant. And so this is the correct way of writing a complex number. Okay, and when you write it this way in the 2x2 matrix format, when you write it in this format, you no longer need to write the letter I. You no longer need to worry about the square root of -1. Okay, this is just, it's really not necessary in order to be able to use complex numbers. So in this 2x2 matrix, A and B are ponderable floating point values. Okay, A and B in this matrix are ponderable floating point values. Okay, notice that I'm not calling them real values, okay, because I want to get rid of the terms real and imaginary, okay, because these terms are confusing the language. They're confusing the language, and they're making people misinterpret phenomenon incorrectly when they look at the equations. So I think it's really important to, let's start from scratch. I cleared the slate, we're going to start over, and this is how we are going to represent complex numbers from now on. Okay, in what I want to do is I want to go back and look at all the places in physics that use complex numbers and start up using this language instead, using this notation instead, and see if it buys us any insights. For example, Euler's formula, e to the I times theta, okay, can be written in the 2x2 matrix format as cos theta sine theta cos theta minus sine theta. Okay, so this is Euler's formula in the 2x2 matrix format. And so written with the 2x2 matrix format, you don't need I. Okay, so you can get rid of the imaginary identity, because the imaginary identity is embedded into the 2x2 matrix. And so you can see here the very beautiful 2x2 matrix formalism of Euler's of e to the I times theta. And so I actually think this is very beautiful. I really like it. I think it is super easy to understand. You've got the real component on the forward diagonal. You have the imaginary component on the backward diagonal. Each component is is calculable. You can calculate each component is going to evaluate to a floating point okay, I don't want to use the word real, I'm trying hard not to use the word real, to a floating point value, to a ponderable floating point value. So by ponderable, I mean it's not infinity, it's not some imaginary character I. It is a value that we can plug into an equation. This is basically an equation. Okay, this is the same equation as, let me just clean this slate a little bit. So this is the same as cos theta plus I sine theta. So that is also cos theta sine theta minus sine theta. Okay, so these are also the same thing, and this is Euler's formula. Okay, so, but this is, you don't need to even remember this stuff anymore. This is all you, to be able to do math in my world, this is the only thing you need to remember regarding Euler's formula. Okay, this is going to work perfectly fine. It's going to work perfectly as long as you do all your math in the proper 2x2 matrix format, which is actually pretty simple to do once you learn how to do it. It's just a game you can play with your kids to teach them how to add and multiply complex numbers, two-dimensional numbers. But there's nothing mysterious about it. There's nothing imaginary about it. And this is, you know, as transparent and clear and unambiguous as you can get as a representation for complex numbers and for Euler's formula in particular, in my opinion. So I'm going to clear the slate again, and I'm going to write this down, Euler's formula, but nice and big, and I'll try to be neat and tidy here. So cos of theta goes on the forward diagonal, and sine of theta goes on the backward diagonal. Okay, so this is Euler's formula in the 2x2 matrix format. And so matrices have square brackets generally in the scientific literature and mathematical literature, so I am sticking to that format. And so this is the formula that is used. This is also the formula, Euler's formula is the one that is used by electrical engineers. Okay, and they refer to it as a wave function. This is a wave function. Okay, this is a wave function. I'm not drawing that very well, but anyways, so this is a wave, this is the wave function. This is a wave function, and this is the wave function. Okay, there is no other wave function. This is the function of a helix wave. Okay, it's got both the cos and the sine are orthogonal to each other, and so this is the equation of the wave function. And in the electrical engineers, they often write it as, let's see, where can I write this? A e to the I times 2 pi f t. Okay, so this is what they write. This is what they write, and this would be the 2 pi f t is really the phase of the wave. Okay, so this is what electrical engineers use, this equation here. They don't use any other wave equation. Okay, but this wave equation doesn't match the wave equation of the that they use in quantum mechanics. Okay, that they use in light theory, that or derived from Maxwell's equations. Okay, so the plane wave equation has a problem, in my opinion, and I believe the problem is because they weren't using the 2x2 matrix formalism of complex numbers, and in So in the research I did, it seems that that they were really convinced that imaginary numbers, square root of -1, you can't understand that imaginary numbers weren't important, shouldn't exist, we don't know what they are, we don't know what they're for, and they tried to eliminate them. Okay, and a lot of physics, they're constantly trying to eliminate the imaginary component by multiplying by the complex conjugate or using other means. And then when you do that, you're just left with two real cosine terms. So here's what I'm talking about. The wave equation for light, which is on the left here, is completely different than the wave equation for all other wave phenomenon. Okay, all other wave phenomenon, including radar, which is light, okay, it satisfies this formalism. So this formalism completely describes and predicts the behavior of wave phenomenon, and radio waves being a wave phenomenon. So why all of a sudden would light be subject to different laws? Why would light be subject to a different wave equation? How could that possibly be? Well, it looks like they were trying to somehow get rid of the imaginary component. Okay, they got rid of the imaginary component through just ignoring it, or sometimes they take the complex conjugate and then you end up with a negative value, but you end up with a real value. So this whole concept of real and imaginary numbers, we have to convert the imaginary to real numbers in order to get a real value. When you look at this 2 by 2 formalism, the imaginary values are also ponderable floating point values, real and ponderable values. And so there's no need with a 2 by 2 matrix formalism, there's no need to convert back to real numbers because you've got all the numbers here. There's nothing being hidden. You know exactly what's going on. And so I'm just wondering what's going on here. It looks like they tried to develop a formalism by canceling out or somehow ignoring or getting rid of the imaginary component, and then they end up with just cosine terms, real, okay, what they're calling real, which is really just the forward diagonal of a 2 by 2 matrix. But it looks like here they are doing something funky here. This does not correspond to the standard wave function as defined by Euler's formula. This is still e to the I times theta. Okay, so this is the wave function for all wave phenomenon, and this is something completely different. It's something completely different, and I think because the electric and the magnetic are orthogonal principles. They're incommensurate principles. They're orthogonal in principle, but they're not orthogonal in space like this. This is a graph of something that's not physical. Okay, this is a graph of what happens when you throw the baby out with the bathwater. That's what they're doing. Okay, they're throwing the baby out with the bathwater. Okay, when they try to in physics, I know they do it in quantum mechanics, and they do it in this derivation here. I'm pretty sure they're throwing the baby out with the bathwater by ignoring the imaginary component, which is a very important part of the equation. Okay, it's there. The imaginary component is there, and it means something. The backward diagonal of a 2 by 2 matrix in computer graphics generates rotations. Okay, it's a rotar. Okay, it rotates. So the forward diagonal is a scalar. The backward diagonal is a rotator. It rotates things, it spins things, and that is why, things like electrons and subatomic particles have spin, because spin is built into the equation in the imaginary component of the 2 by 2 matrix. Okay, and so I made a big mess here. Sorry about that. I'm going to clean it up a little bit. But I think you see the point I'm making is that by ignoring the imaginary component of, say, A plus BI, and by calling this imaginary, and then by assuming that imaginary numbers are not important, or that we have to somehow eliminate them so that we can end up with real values, is the, okay, wait for it, okay, ignoring the backward diagonal of a 2 by 2 matrix and trying to constantly get rid of the imaginary component of a complex number is the biggest blunder in theoretical physics in terms of interpretation. Okay, it's caused a lot of confusion. It's completely unnecessary. We don't need that language. The backward diagonal of a 2 by 2 matrix is easy to see. It's easy to understand. Okay, the only thing you have to understand is that the forward diagonal and the backward diagonal are opposite sense in the 2 by 2 matrix. Okay, so let's clean that up a bit. Okay, so this is an imaginary number, but it's not imaginary at all. I could put a 10 here and a minus 10 here. I can put ponderable values in here and understand. I know what this means. And I can put ponderable values in here, say 100, 100. I can do that, and this is still a complex number. Right, as long as the forward diagonal is the same sense and the backward diagonal is the opposite sense, this is a complex number. Okay, so ignoring, not realizing that complex numbers are two-dimensional numbers, I believe, and not realizing that the imaginary number is the backward diagonal of a 2 by 2 matrix is the biggest blunder. That, the biggest mathematical, the biggest physics blunder, the biggest scientific blunder in terms of interpretation. Okay, it's mostly to do with interpretation. They are misinterpreting things because they are assuming that imaginary numbers are not real. And so using the terms real and imaginary have really created a language problem. And so I'm trying to fix that by, I want to ditch these terms. I don't ever want to write I for an imaginary number. I don't need to. Okay, I only need to do this. Okay, that is my formalism for complex numbers. I don't need I don't need square root of -1, okay, and I don't need the confusion that that language causes. And so that's all I'm going to do for now. I just wanted to get that out there because it was really bothering me. I wanted to make this video for a while. And so, basically, I would like to see how we can apply this to all the other confusing languages such as relativity and quantum mechanics, and of course I'm working on that. But if you want to work on that as well, I think I have put up enough information out there about complex numbers to give you the tools that you need to reformulate. What I want to do is reformulate all of the confusing languages into this formalism, so that we can maybe get a better understanding about how nature works. All right, ciao for now.